Factor the following polynomials completely. So again, today's lesson was seeing structure, advanced factoring. We're going to be looking at expressions that look familiar, but it's not just going to be a plain old x sitting there that I want to factor. So I have x plus 3 squared plus 3 times x plus 3 minus 10. So if I'm looking at this, I have something squared, n squared, plus 3 times that same thing, minus 10. These expressions have the same structure. Instead of an n, though, I have an x plus 3. So, how do I factor n squared plus 3n minus 1? Well, you can go through do the AC method, but because the leading coefficient's 1, what numbers multiply? What numbers multiply to negative 10 that add to 3? Well, that's positive 5 and negative 2. So that's how I factor that expression. This expression's basically the same, but instead of an n, I have an x plus 3 plugged in. So I have x plus 3 plus 5, and then x plus 3 minus 2. And simplifying those, I get x plus 8 times x plus 1. So I can factor that expression as x plus 8 times x plus 1. You could go through and expand that out, simplify it, and then factor, but you're going to waste your time looking for and making use of structures much simpler. Number 2, 2x squared minus 7x squared minus 2x squared minus 7x minus 12. So again, look at the structure of this. I have something squared minus that thing minus 12. Something squared minus that term minus 12. I know how to factor this expression. The leading coefficient of 1, what multiplies to negative 12 that adds to negative 1? Well, negative 4 and positive 3. You get negative 12, negative 4, and positive 3 add to negative 1. So I have this expression here, but I don't have an n. N's just being my placeholder for 2x squared minus 7x. So this is 2x squared minus 7x minus 4 times 2x squared minus 7x plus 3. Well, now I have two quadratic polynomials that maybe I can factor. How am I going to factor these? Well, I have leading coefficients here, so I'm going to have to use the AC method. What multiplies to a times c? What multiplies to negative 8? That adds to negative 7. Well, that's negative 8 and positive 1. So I get 2x squared minus 8x plus 1x. I'm just splitting that term apart there. That negative 7x, I just split it into two different terms. Group them now. Look at the first two. I can take out a 2x. I'm left with x minus 4. Look at the next two. I want an x minus 4. Well, I currently have that, so I'll take out a positive 1. So, factoring out the GCF of x minus 4, I'm left with x minus 4 times 2x plus 1. Maybe you can do this by guessing and checking, but this AC method will always work. Now let's look at the second trinomial over here. Leading coefficient's not 1, so what multiplies to 6, 2 times 3, that adds to negative 7. Well, that's negative 6 and negative 1. Negative 6 times negative 1 gives me 6, and that adds to negative 7. So I'm going to split that middle term apart as minus 6x minus 1x plus 3. Group them. From the first two terms, I can take out a 2x. What times 2x gives me 2x squared? X. What times 2x gives me minus 6x minus 3? So I want an x minus 3, so I'm going to have to take out a negative 1 to get that x minus 3 over there. Now x minus 3 is a common factor, so I can factor that out, and I'm left with 2x minus 1. So that original crazy expression up there is actually equivalent to x minus 4 times 2x plus 1 times x minus 3 times x minus 3 times 2x minus 1. It's equal to the product of those four linear factors. I took this crazy expression, looked at its structure, and found it's the product of those four linear factors there. Number 3, x squared minus 3x plus 1 squared minus 1. Hopefully you recognize this as the difference of perfect squares. This first thing is something squared minus 1 squared. So this really is n squared minus 1. Well, I know that factors as n plus 1 times n minus 1. Well, what's n in this case? N is that quadratic trinomial there. So that expression up there is actually x squared minus 3x plus 1, that's my n, plus 1, times x squared minus 3x plus 1 minus 1. Simplifying, I get x squared minus 3x plus 2, x squared minus 3x plus 0, so I'm just not going to write that. Looking at this first trinomial, x squared minus 3x plus 2, well, that's x, what multiplies to 2 that adds to negative 3, because I have a leading coefficient of 1. So this one should be quick. What multiplies to 2 adds to negative 3? Well, that's negative 2 and negative 1. And this next term, well, there's no constant term. Is there anything I can factor out? Yeah, I can factor out an x. So my final answer is x times x minus 2 times x minus 1 times x minus 3. That expression up there is equivalent to that expression down here that I wrote. Looking for and making use of structure makes you recognize quickly that it's really just the difference of perfect squares. Number 4, 8x to the 6th plus 7x cubed minus 1. Well, this looks awfully a lot like 8n squared plus 7n minus 1. But instead of an n, you have an x cubed plug in there. So let's factor this and then plug in an x cubed. Well, my leading coefficient's not 1, so I should probably use the AC method, unless you like guessing and checking so much. What multiplies to a times c, what multiplies to negative 8, that adds to 7. Well, that's 8 and negative 1. Great. So now I'm going to split that middle term apart. 8n squared plus 8n minus 1n minus 1. Group your terms. Well, I can take out an 8n from there, and I get n plus 1. So I want to end up with an n plus 1 over here. What do I need to factor out? Because I currently have a negative 1n minus 1. I'm going to factor out a negative 1. I'm going to factor out an n plus 1, because that's the common term, times 8 minus 1. But I don't have an 8. I don't have an n. I have a x cubed. If I plug an x cubed into here, I'll get that original expression. So this is really x cubed plus 1 times 8x cubed minus 1. If I go through and multiply that out, you will get that original expression there. But we always want to factor completely. Are we done? No. Hopefully you recognize both of these as the sum of perfect cubes and then the difference of perfect cubes. So that first term factors as x plus 1. It's the sum of perfect cubes. X squared minus x plus 1. And then the second term, well, that's 2x raised to the third power. That's 2x cubed. So I get 2x minus 1, same sign, times 2x squared, which is 4x squared, plus the product, plus 2x, always positive, 1. That's how I'm going to factor that expression completely. I'm looking for and making use of structure saying this looks like 8n squared plus 7n minus 1. Number 5, explain how the expression in exercise 2, which I've copied here, is related to the expression n squared minus n minus 12. Well, we use this. Now I just want you to write it out in words that instead of having a 2x squared minus 7x, I have an n. This is something squared minus something minus 12. Instead of using a chicken nugget like we did in class, I used an n. So they're related, they have the same structure, but this one just has a 2x squared minus 7x plugged in wherever I had an n in that expression. Number 6, factor u cubed minus u squared minus 9u plus 9. Explain how you can use this result to factor this expression. So first, let's factor this here. U cubed minus u squared minus 9u plus 9. So it's a cubic polynomial. 99% of the time, we're going to factor it by grouping. Well, what can I factor out? Well, from the first two terms, I'm going to take out a u squared. and I get u minus 1. From these next two terms, I want a u minus 1, so I'm going to factor out a negative 9. Negative 9 times u gives me negative 9u. Negative 9 times negative 1 gives me positive 9. Both of those terms have a u minus 1, so I'm going to factor that out front. What am I left with after I undistribute that u minus 1? I'm left with u squared minus 9. Well, what's u squared minus 9? That's the difference of perfect squares. U plus 3, u minus 3. So, how can I use that factorization to factor that expression there? Well, that expression is still something cubed minus something squared minus 9 times that something plus 9. So it's the same exact structure, but instead of a u, they plugged in an x plus 2. So that expression is equal to x plus 2 minus 1, u minus 1, times u plus 3, so x plus 2 plus 3, and then x plus 2 minus 3. They have the same structure, but instead of a u, it's an x plus 2. Simplifying, we get x plus 1 times x plus 5 times x minus 1. That's how I factor that expression completely. Number 7, factor the expression completely. So, this is a cubic polynomial. I'm first going to ask, is there a GCF? 8, 4, 18, and 9? No, other than 1. So I'm going to try grouping. The first two terms, 8x cubed plus 4x squared, well, I can take out a 4x squared from there. You always want to take out the greatest common factor. What times 4x squared is 8x cubed? Well, that's 2x. 4x squared times what gives me 4x squared? Well, plus 1. So when I group these next two terms, I want to end up with an x plus 1 so I can factor that GCF out. Well, what do I need to factor out from there? A minus 9. These two expressions are equivalent. They just look different because I grouped them and factored. Well, now both of these have a 2x plus 1 as a factor, so I'm going to bring that out front. And I'm left with 4x squared minus 9. Ask yourself, is this factored completely? Well, 2x plus 1, that's a linear term, that's factored completely. But 4x squared minus 9, hopefully that warning light's going off that this is the difference of perfect squares. So I get 2x minus 3 and 2x plus 3. That's how I factor that cubic expression completely into the product of three linear factors. Number 8. Back to our first day of class together, express the product of 2x squared plus 7x minus 10 and x plus 5 in standard form. You have two ways to multiply things. You can use a table or use the distributive property. I'm going to use the distributive property so you kind of see how factoring works, how our factoring by grouping kind of works. You could use a table, you're going to get the same answer I do. I'm going to treat that x plus 5 as one big chunk and distribute it into that trinomial. So I have 2x squared times x plus 5 plus 7x times x plus 5 minus 10 times x plus 5. So when we did grouping that one day, we said, wait a minute, these all have an x plus 5 in them. Let's factor that out. So factoring is just the undoing of multiplication. We're just using the distributive property in the reverse order. Well, now I can apply the distributive property 3 times and get 2x to the third plus 10x squared plus 7x squared plus 35x minus 10x minus 50, and combine my like terms. So I get 2x to the third plus 17x squared plus 25x minus 50. So, unfortunately, I can't group this polynomial to solve it, to factor it, but if I gave you this green expression here, hopefully you could go through and group the terms by 2, and then factor out that x plus 5. Factoring is just undoing the multiplication by the distributive property. So our final answer is in standard form. Notice that its exponents are decreasing. My leading coefficient of 2 there is the coefficient of the highest power. Determine if x plus 7 is a factor of 2x cubed plus 19x squared plus 32x minus 21 by using long division. So, Could you do this by reverse tabular? Of course, but I'm asking you to long divide because I need you to get good at long division, so when we get to things with remainders, it's a little bit easier to use long division than it is to use reverse tabular. So I'm dividing by x plus 7. What times x gives me 2x cubed? Well, 2x squared. 2x squared times x is 2x cubed. 2x squared times 7 is plus 14x squared. Now, I'm going to go through, change my signs to subtract, and I get 0, and then 5x squared plus 32x minus 21. Restart the process. What times x gives me 5x squared? Well, plus 5x. 5x times x is 5x squared. 5x times 7 is plus 35x. To subtract, I'm going to change the signs. 0, 32x minus 35x leaves me with minus 3x minus 21. Restart the process. What times x gives me negative 3? Well, negative 3. Negative 3 times x is negative 3x. Negative 3 times 7 is negative 21. And this looks promising because when I change the signs, I get a remainder of 0. Something is a factor if and only if you get a remainder of 0. Because what this tells me is this polynomial, 2x cubed plus 19x squared plus 32x minus 21, can be written as, I can factor it now as x plus 7 times 2x squared plus 5x minus 3. I can now factor this polynomial because I know that x plus 7 is a factor, and it's a factor because our remainder was 0. And what's even cooler is I couldn't group this. There's nothing I could factor out from here to group it using factoring by grouping. But because I know that x plus 7 is a factor, I can now factor that trinomial. What multiplies to negative 6 that adds to 5? Well, what multiplies to a times c that's negative 6 that adds to 5? Well, that's 6 and negative 1. So I know that this is x plus 7 times 2x squared plus 6x minus x minus 3. That's x plus 7 times 2x times x plus 3, negative 1 times x plus 3. So the three linear factors are x plus 7, x plus 3, and 2x minus 1. This is something that we're going to be doing towards the end of the unit, is taking these cubic polynomials, factoring them by kind of this division process, because now I can easily graph this cubic polynomial, and that's what we're going to be focusing on towards the end of this unit. So, by expressing something as the product of its linear factors reveals so much information about its graph. And finally, number 10, solve x squared minus 8x equals 24 for all real values of x. So, it's a quadratic equation. I have three options. I can factor it, I can complete the square, or I can use the quadratic formula. Regardless of what you do, you're going to want to set your quadratic equation equal to 0. First thing I always check for is, can I factor it? Well, is there a GCF? No. Okay, well, the leading coefficient's 1, so what multiplies to negative 24 that adds to 8? What multiplies to negative 24 that adds to 8? Unfortunately, nothing. There's not any nice integers that do that. So you either have to complete the square, which I know that none of you remember. If you do, you're awesome. So let's use the quadratic formula. My a value is 1, my b value is negative 8, my c value is negative 24. So we compute x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So x equals negative 8, so 8 plus or minus the square root of, well, what's negative 8 squared? That's 64 minus 4 times 1 times minus 24 all over 2 times 1. 8 plus or minus the square root of 64 plus 96. 64 plus 96 over 2. Well, 64 and 96 gives me 160. What's the square root of 160? What's the biggest perfect square that goes into 160. Well, that's 16 and radical 10, so this is 4 radical 10. X equals 8 plus or minus 4 radical 10 over 2. Well, is there anything I can factor out of the numerator to divide it by 2? Yeah, I can factor a 2 out of the numerator and get 4 plus or minus 2 radical 10 over 2. Dividing by 2 leaves me with my two solutions of 4 plus 2 radical 10 and 4 minus 2 radical 10. Again, this is just a review of using the quadratic formula because we're going to need to use the quadratic formula at some point in this course to solve quadratic equations again. That's it.